When you go to an amusement park, you might see these two rides. So we have talked about roller coasters a lot in the energy unit. For this unit, we're going to look at carousels and solve some problems because they're going to cover circular motion and they're moving in a circle. So let's talk about circular motion. Circular motion is defined as you can see from the name, object moving in a circle, and it's moving. So we're going to look at its motion when it's moving in a circular path. So for this class, we're going to define the uniform circular motion, or UCM abbreviation for uniform circular motion. What it means is that the object is moving in a circle, but it's moving with a constant speed, or the speed is not changing. So we're going to take a look at some examples of circular motion. Let's say we have a bagel tied to a string and we are moving it around on top of our head in a circular path. So that's one example of a bagel on a string observing circular motion. Next, you might have noticed that Earth moves around the sun. We're going to consider it circular path, but we already know it's kind of an elliptical path. Another example is you can have a hoop and place a marble in the hoop and kind of make it move around the edges of the hoop, and that's also going to follow a circular path. So that's another example of an object moving in a circle. Or it's not too safe, but if you move a car in a circle, it's also going to experience some circular motion when the car has been driven in a circle. So now when we're talking about all these examples, we're going to look at each example and kind of define what's going on in the motion. So as you can see, all the objects are moving in a circle and they're all going to be considered as moving at constant speed. But if you look at an instant, the velocity is actually changing. That's because the speed, the magnitude is staying the same, but the direction of the velocity is changing, which means that if there's some velocity changes, there has to be some acceleration. So if you notice an object moving in a circle, notice how the velocity is changing at each point. If you look at the instantaneous points, the velocities are changing. So that's why we say that this object is being accelerated. Now if there's some acceleration, we know that according to Newton's second law, there has to be some net force. So if there's some acceleration, then there should be some net force according to Newton's second law, which means that there is some net force in these scenarios. Now let's take a look at each scenario and see what forces we see. On the bagel, we see there's some tension force along the string. There's some gravitational force from the Earth to the sun. There's some normal force from the hoop to move the marble in a circle, and there's a friction force to keep the car in a circle. And those are the forces that we notice in these examples. Now all of these net forces are causing some net force to make the object move in a circle, and that's defined as centripetal force. Now if we have to define centripetal force, it's defined as the force that acts toward the center of the path, which causes it to move in a circle. As you can see, the bagel moving in a circle is due to the tension force along the string, but that's the centripetal force. The Earth moving around the sun is also caused by gravitational force, so that's the centripetal force causing the Earth to rotate around the sun. Similarly for the ball in a hoop and a car driving. Now let's break down the word centripetal into two parts. Centri means center and petal means seeking. So that's where it gets the meaning of towards the center. So when we use the word centripetal for the force, we always mean that force is towards the center. So now if centripetal is the force is the net force or towards the center, so it means that it should be, according to Newton's second law, have this acceleration also towards the center of the circle. So we're going to use the symbols AC and FC for centripetal, acceleration, and force. And now we're going to take a look at the equations. So I'm not going to derive here, but I will just give the equation for centripetal acceleration. and that's v squared over r. So plugging it in Newton's second law, we replace the a with the v squared over r, and we get the equation for centripetal force, where v is the speed and r is the radius of the path of the circle. Now when we're talking about speed, we already know that speed is defined as distance over time. And if you look at the path, which is a circle, and if an object is moving in a circle, it's actually traveling around the circle. And if you remember, the distance that it travels around the circle is called the circumference. And we are going to introduce another term for the time that it takes to move around the circle. So since we're going to take the time moving around one time around the circle, we call it the time period, or the time it takes to travel one circle around the circle once. So that's the time period term that we introduce with this speed. Alright, I'm going to put it down as circumference, and this is called the time period. So for the time period, we have to always figure out what is the time that it takes to complete one rotation around the circle. So let's look at another form of equation that we can derive from plugging in the speed equation. And if you simplify this equation by canceling the r on the top, you get another equation which for centripetal acceleration, which is 4 pi square r over t squared. So that's another centripetal acceleration equation. Now we're going to focus on the equations for circular motion, and I'm going to put it down so that you can remember to use those equations. This equation, first one, is for centripetal acceleration, second equation is for centripetal force, and the third equation that I've written is the speed